Right, hello everybody, I'm Alex. I'm studying mechanical engineering at the University of Southampton, and my research was using a physics-informed machine learning approach to predict indoor temperature for homes with air source heat pumps. So the aim was to develop a model which combines building physics with machine learning to accurately predict indoor temperature. Models like this have massive benefits for the environment because space heating accounts for a massive proportion of UK energy demand, but it also enables much better thermal comfort and enables energy flexibility as well. So to do this, we used a three-stage approach. So firstly, we created a reference model which gave us a baseline prediction based purely on building physics. We then extended this to a hybrid model using a neural network to improve the accuracy of the prediction. And then we explored the use of transfer learning to essentially leverage knowledge across similar homes so we don't have to continually retrain the models. So for the study, we used 64 homes which had been retrofitted with air source heat pumps. We focused on one heating season. As you can see from the bottom left, the majority of our households were detached, but we also had semi-detached, terraced and bungalow properties as well. And we took data from the heat pump itself, the weather for each household, and we had access to simple building metadata, so the floor area, building age, etc. So for the first model, the reference model, we represent each household as a single thermal zone being encapsulated by a square building envelope. And we use a resistance capacitance model to essentially model the thermodynamics for each building. So in terms of the model inputs, we have the mechanical heating from the heat pump. We have the solar and internal gain, which is shared across both the indoor temperature node and the envelope temperature node. And then we have the fabric heat loss, which is represented by the blue arrow across the two thermal resistors on the right. And then we have the ventilation heat loss, which is directly from the indoor temperature to the ambient. And obviously we're trying to predict the indoor temperature. So to calculate the parameters for each home, we obtain the thermal output power directly from the heat pump data. We could calculate the solar gain from our weather data, and we used ISO occupancy schedules to essentially calculate the internal gain. Ventilation resistance was used with an assumed infiltration rate, and then we had a set of RC parameters which were specific to each household, which we needed to calculate, but due to the lack of building data, we weren't essentially able to calculate them exactly. So we used a Bayesian inference procedure to calculate them. So we firstly calculated an initial estimate, which we then used with a week of training data to essentially create an optimized distribution for each one. So if you see on the right-hand side, we calculate a initial estimate, which we represent as a probability distribution with a wide standard deviation. And then our algorithm essentially tailors that using the week of data to a much more accurate value with stronger confidence, hence a narrow distribution. And then we extend this with the hybrid model, so we use a long short-term memory neural network to essentially, which is trained on the difference between the baseline model and the true indoor temperature. So it's trained on a week of that, and then it can predict that into the future, so it essentially corrects the baseline prediction to a much more accurate value. So rather than completely training a neural network, which a lot of studies have done in the past, we use a physics-informed neural network, which is a lot more interpretable because we can understand why the model's making the predictions it is. And we can also quantify the uncertainty due to our Bayesian framework. So this is a comparison of the results for the first two approaches. You can see the dashed blue line at the top left, that's our reference model. So we had a root mean squared error of 1.4 degrees Celsius, which was improved by 68% with the neural network, which is the green dashed line at the bottom left. We also tested both of our models during a deferral event. So when the demand's too high on the electricity grid, we essentially have to turn off the heating power for the air source heat pump. And you can see that it's able to track the decline in temperature inside of the house as well. And that was with an error of 0.3 degrees Celsius, so very accurate. So in terms of transfer learning, the aim here was to essentially, once we have a set of well-trained models for a group of houses, rather than retraining it for another home, we can leverage the knowledge the model already has for a similar home. So we group the homes into clusters using the building age and floor area. We have 7 groups. And then within each cluster, we form a distribution which is the average of the parameters, which can be used as an input rather than us calculating a rough estimate. And as such, the algorithm converges much more quickly, and it gives us a much more accurate parameter. So as such, we generate more accurate temperature predictions. So the right-hand side, you can see the box on this plot, which shows the results for this. So compared to last time with our resistance capacitance model, the green box, we have a mean of 0.9 degrees Celsius, so a clear improvement of 35%. The blue box at the bottom is the average, so our standard case where we just do the full training. And then the red box is where we use the neural network for a brief retrain, but as we recalibrate again. which obviously gives us the best accuracy because we're combining the transfer with a retrain as well. So that was the best accuracy we had, 0.39 degrees Celsius. And we also found that essentially the training was much more quick because the prior and posterior distributions were much more close, so the algorithm converged much more quickly. So to summarize, we created an interpretable baseline resistance capacitance model, which gave us temperature predictions with acceptable accuracy, but were greatly improved by the addition of a neural network, bringing us down to 0.44 degrees Celsius error. And then we use clustering and transfer learning to essentially leverage knowledge from similar homes to other homes so that we don't have to continually retrain the model for different households. And it doesn't matter if the household doesn't have much data available. So in future, we're looking to essentially use these temperature forecasts with model predictive control algorithms to devise heating schedules which enable us to reduce the peak demand on the grid and spread the demand when the peak is really high, for example, in winter evenings. So yeah, I'll finish up. Thank you.